Hey everyone, how goes it? Welcome back to Computer Science 552 Game Development. Today we're going to continue discussing the next dimension. We turn our attention to the roles of the programmer and the artist, exploring 3D game development. We have established that the graphics pipeline is a model that describes a queue of steps required for a 3D system to draw a 3D scene to a 2D screen. More specifically, the act of drawing a 3D scene to a 2D screen is called rendering. The process can be broken into three sequential steps: application, geometry, and rasterization. The geometry step is responsible for generating the 3D scene from the information provided by the application. This establishes a world or global coordinate system and transforms all 3D objects to fit within it. The concept of transformations have been mentioned before, and it becomes a central feature in all of 3D. All major vertex and triangle operations occur during this step. In relation to this, a shader is a program used to affect the rendering of a 3D scene. The types of shaders include 2D and 3D shaders. 3D shaders are used for a couple of different purposes. One is it calculates the brightness and the colors of a textured mesh surface. Another is it modifies the vertices of 3D mesh. They do a lot of work, but mostly focus on the 3D geometries that are displayed. Shaders occur at different stages of the graphics pipeline. 3D shaders during the geometry step, 2D shaders during the rasterization step. Looking into the geometry step a little closer, we can see that it can be further broken down into 5 steps: mesh and camera transformations, lighting, projection transformations, clipping, window viewport transformation. Each substep handles a different aspect of 3D rendering. These will be discussed in several future lectures. Today, we turn our attention to cameras and projections. We view 3D spaces through the lens of a camera. Cameras require a set of matrices in order to draw the 3D scene onto a 2D screen. These are the world matrix, the view matrix, and the projection matrix. The world matrix for a 3D camera is the transformation matrix of the camera. A 3D camera is a 3D object within the world space, so it has a position, rotation, and scale. A camera is not considered to be a mesh, and it is usually considered to be a single point. The view matrix for a 3D camera establishes the view space of the camera. It centers the origin to be the camera and defines the directions. Up is a unit vector that points along the y-axis. Right is a unit vector that points along the x-axis. Forward is a unit vector that points along the z-axis. In Unity, it is the green, red, and blue arrow respectively. We can see the view matrix representation here. As we must view this through the lens of a camera, all 3D objects have local coordinates that are transformed into camera coordinates. The camera is assumed to be at the origin 0, 0, 0, and this is for simplicity's sake. A 3D object's coordinates are now relative to the camera. The projection matrix maps the 3D scene to a 2D screen. It transforms from the view space to a projection space. Camera coordinates become clip coordinates. This is based on the camera's view area, which can either be a box or a frustum. By the way, a frustum is a pyramid with the top part chopped off. These transformations are not affine transformations, they're projective. There are two common projections: orthogonal and perspective. Orthogonal projections assume that the camera's view area is a box. The box's property is a width, the distance in the x, a height, distance in the y, z near, a local coordinate of the camera's lens, and z far, local coordinate representing the distance the lens can observe. These projections flatten 3D models to the screen. We can see a simple implementation of an orthogonal projection matrix here. We can see in the image the application of the orthogonal matrix. Notice how both cubes appear to be flat, or just simple rectangles without any 3D form. Perspective projections assume that the camera's view area is a frustum, similar to hallway or one-point perspective drawings. It is one way we can represent the visual element of form or the 3D properties of an object. The frustum's properties is a field of view x, which is the field of view angle in the x direction. The field of view y is the field of view angle in the y. Z near is again the local coordinate of the camera's lens. Z far is the local coordinate representing the distance that the lens can observe. These projections provide a more realistic view of the world. We can see the more complicated matrix used to implement a perspective projection. Now, we can see it represented where we notice that the cubes appear less flat. Seeing this side by side, we can see how the orthogonal projection flattens the object to its plane, whereas a perspective provides more dimension. One detail to keep in mind is that we frequently use both orthogonal and perspective projections, but commonly for different purposes. For instance, orthogonal projections can be used in 3D modeling software to more easily work with vertices, edges, and faces. The perspective projection is used in the game engine to display those models, providing more dimension. To explore this further, let's look at the representation of projections in 3D software and game engines. Here we have our 3D software Blender, where we can use different cameras to create 3D meshes. By default, we have the perspective camera. However, by pressing number pad 1, 3, or 7, we can quickly switch to orthogonal views for either the front, right side, or top, respectively. We can see from this top view how everything has been flattened to the plane. Now, we can switch back to our perspective by using the middle mouse. Going back to the top orthogonal, we can now enter edit mode. And turning on snapping, we can more easily and precisely edit vertices, edges, and faces. We can also see the camera in Unity. We can see in the inspector when we switch the 3D camera from perspective to orthogonal. This can be used to give our games different visual effects. Depth map is usually created alongside the projection. This is created using the depth buffer or the Z buffer, which represents the distance information regarding surfaces of a 3D object. In this case, it is the distance from the camera pointing along its Z-axis to the object within its view space. This assists in identifying objects that are hidden or occluded behind another one. This helps speed up the rendering process by skipping surfaces that cannot be seen. All 3D objects' local coordinates are transformed into the camera coordinates. Camera coordinates are then transformed into the clip coordinates. Clipping removes or culls unnecessary rendering steps for the sake of speed. Viewport culling or box frustum culling removes any object that is outside of the camera's view space. Backface culling does not draw triangles whose normal faces the same direction of the camera. We can see the formula here. We can understand the VN is a vertex on a triangle. C position is the camera's position. N is the normal of the triangle's surface. And DOT is the dot product between the vectors that are formed. If we understand the dot product, then this starts making a lot of sense. We can understand that the dot product between two vectors results in a scalar length, which represents the projection length or shadow length of one vector onto another. When this value is greater than 0, then the camera's vector and the face's normal are facing the same direction. Only faces whose normals face toward the camera or would have a negative dot product are drawn. Depth clipping or occlusion clipping or Z clipping skips over rendering triangles that cannot be seen because they are too near or too far or hidden by another object. It uses the depth map to assist this. The Z distances are used for these tests. Simple depth clipping uses near and far properties of the view space. More advanced algorithms use 3D geometries and projections to skip hidden triangles. Finally, the window viewport transform converts the clip coordinates into screen or device coordinates. Generally, a window in screen coordinates contains a viewport showing an object oriented using world coordinates. The world coordinates being wx, wy, which would also have the properties w width, w height. The viewport coordinates vx, vy, and also has the properties vmax z, vmin z. These correspond to the far and the near distances. These coordinates are then sent to the rasterizer. All 3D objects' local coordinates are transformed into camera coordinates. Camera coordinates are then transformed into clip coordinates. Clip coordinates are then transformed into screen device coordinates. Screen coordinates are then sent to the rasterization step to finally be drawn to the screen. We can consider that the screen coordinates to be a rendered 2D image from the 3D scene, and now it must be displayed on our screen. Rasterization applies the projection and clip coordinates onto the 2D screen. As mentioned before, raster is German for grid. A screen is divided into a grid where each point is called a fragment. A screen buffer is a grid or matrix data structure used to represent each fragment. One picture element is one pixel, which is one fragment. The size of the grid is based on the pixel width and height of the screen or the screen's region. Rasterization fills the screen buffer with the provided screen coordinates. Overlapping objects use the Z buffer to determine which is to be drawn. Closer objects, the smaller Z values, are drawn on top of objects that are further away. The screen has a discrete number of pixels while the scene is continuous. Aliasing occurs when there is a loss of resolution, and anti-aliasing assists in smoothing these features. Pixel or fragment shaders occur during this step. For instance, motion blur and other post-processing effects. We use transformations to convert from one coordinate space to another. 3D meshes or models have their own coordinate space that needs to be transformed into the world space. The world's 3D space is transformed then into the screen's 2D space. All of these require a series of matrix multiplications. These are generally handled by the vertex shaders. We have reviewed many topics related to cameras which have concepts in many different parts of the graphics pipeline. In addition to geometry, we have also reviewed the ideas of the rasterization step. However, there is still more to discuss. Until then, I'll see you next time.